Hi everyone, Mr. Smith here. In this video lesson, we're going to continue our discussion of motion in two dimensions and talk about relative motion. So let's get started. Canada Day was just wrapped up as I'm shooting this video a few days ago, and maybe you have been at an air show, and you've seen these kind of planes fly by, like the snowbirds are a famous group of planes where they fly in a constant formation and do some maneuvers. And from looking on the ground, these maneuvers appear, and they're like, I'm not trying to minimize it, they appear like very daring, moving back and forth, and they're all kind of moving together. And it's you might wonder why nobody gets hurt, or why they don't get hurt more often. But if you were in the cockpit of one of those planes, what you would see is that even though those planes are flying at a very high speed, they're just all flying in a straight line together. They're not moving at all with respect to each other. It's because on the ground, we are in one frame of reference, so we see the motion in one way. The pilots are in a different frame of reference, and they see the motion another way. Everybody watching this video has probably had some experience driving down a highway. You might be moving at 100, 120 kilometers per hour, extremely fast. And, you're densely clustered with a whole bunch of other cars traveling at the same speed all around you. And you might seem like that's very dangerous. And of course it could be. But, when you're in the car and you look around, and in the car's frame of reference, all the cars are traveling, since they're traveling at the same speed, it looks like nobody is moving with respect to each other. And from a car, it seems quite safe. So today we're talking about frames of reference and relative velocity. The velocity that you might see something moving at might not necessarily match with somebody else in a different frame of reference. Let's continue. I've mentioned this word frame of reference. What is a frame of reference? It is a coordinate system relative to which motion is observed. So in the air show example, we had people observing motion with respect to the ground, and we had probably the second frame of reference in that example would be someone in the cockpit, and they both see the motion in different ways. It's often convenient to use a frame of reference that is stationary. So for example, when considering the motion of a point on a wheel, not the wheel itself, but actually if you track the point on a wheel, the motion you get is actually a fairly involved, like, mathematical curve, where you almost have these repeating semicircular arcs repeating over and over as the wheel moves forward, and this point rotates around the wheel. So that can be fairly complex motion to analyze. However, if you just use the wheel, the center of the wheel, as your frame of reference, if you could imagine you being transported there and actually being on the center of the wheel and moving along with the wheel, what you would see is just the dot moving around you in a circle. And that motion is a lot easier to analyze. So when when we're describing, say, the motion of Mars around the sun, we would use the sun's frame of reference, because the motion of Mars around the sun from the sun's frame of reference is pretty standard. It's, for the most part, just elliptical, and we can make predictions. It's easy to see. From the Earth's frame of reference, Mars is doing a lot of zigging and zagging, because as Earth is rotating around the sun, or revolving around the sun, so is Mars, and the motion can be quite complicated. So choosing a convenient frame of reference is really important. So I threw around this term relative velocity. It's the title of our lesson for today. Relative velocity is the velocity of an object relative to a specific frame of reference. So as I mentioned, the people on the ground might observe those planes flying by at hundreds of kilometers per hour. But for somebody in the cockpit looking by at those other planes, the velocity of the planes around the other plane would be zero. They're not moving at all. So it depends on your frame of reference. And relative velocity is the velocity object relative to a frame of reference you're talking about. So we're going to look at relative velocity examples where we have two frames of reference for the most part. And to analyze relative velocity in more than one frame of reference, we're going to use the symbol for relative velocity, so just velocity vector, but we'll have two subscripts in capital letters. So the first subscript is going to represent the object whose velocity is stated relative to the object represented by the second subscript. So the second subscript is the frame of reference. So let's do a simple example here. So if a car passes by a stationary police officer at 90 kilometers per hour, so we might say this. So, in words, we might say, I'm just going to write this out for now. The relative velocity of the car with respect to the police, so I'll just use a short form WRT for with respect to the police. So that can be quite a handful to write out. So the short form of saying that is the following. Velocity vector, the relative velocity of the car with respect to the police. So we'd say VCP. And in this question, the police officer would be seeing the car drive by him at 90 kilometers per hour north. So that's the convention we'll use. Frame of reference, second subscript. So we'll get a bit more practice with that. In this example here, I want you to try it. So here we have a sports car passing a transport truck on the highway. So the car is traveling at 100 kilometers per hour and the transport truck at 90 kilometers per hour. So I'll do my best. My drawing gets better and better every time I teach this course. There's our big transport truck, not too bad. And it's driving at, let's just say north is to the right here, traveling at 90 kilometers per hour. Then we have the car traveling at 100 kilometers per hour. So clearly, the car is going to overtake the truck. So can you predict the following relative velocities? So I might not even read out what these mean to see if you can grasp what this notation means. So if you want to pause the video and unpause it when you're ready, can you predict these two relative velocities? And we'll unpause it when you're ready and we'll take them up. Or you can follow along right now. So what's the velocity of the car with respect to the truck? So in the truck's frame of reference, how fast does that truck see the car moving? Well, if you're in the truck, and you can imagine when somebody slowly overtakes you on the highway, you see them moving past you at a relatively slow speed. And that speed that you see them moving past you at is the difference between your two speeds with respect to the ground. So the truck is going to see this car drive by. Where's my cursor? There it is. At 10 kilometers per hour north. That truck slowly sees the car pass him in the north direction. What would the velocity of the truck with respect to the car be? Well, as far as the car is concerned, that truck is reversing towards him at 10 kilometers per hour. It would be, you could say it's minus 10 kilometers per hour north, or you could say it's 10 kilometers per hour south. And this is an important point, is that you guys should take this down. It's relative velocities for opposite frames of reference or opposite vectors. Opposite frames of reference or opposite vectors. And this simple example kind of illustrates why. All right, so we've done a little one-dimensional example, but we just kind of basically eyeballed the solutions here. So we want to eventually talk about, well, how can we actually calculate these? Do we have some kind of formula, equation, kind of tool we can use? So in general, we could have calculated the velocity of the car with respect to the truck in this manner. So I'm going to show you guys kind of two ways so we can think about it. The first way we could think about it is we could have taken the velocity of the car with respect to the ground, which remember is like 100 kilometers per hour, and subtract the velocity of the truck with respect to the ground. And that was 90. And so that would give us our 10 kilometers per hour north that we discussed, right? And here the subscript G I'm referring is to the ground. Now there's a second way we can write that using opposite vectors in our note from before on how opposite frames of reference give opposite vectors. And it actually leads to a little trick, like basically an aid to help you setting up these problems. We could have looked at it this way. We could have said that VCT equals VCG, and I can rewrite that previous equation as vector addition by taking the opposite vector, VGT. And I would have got the same thing. So this kind of chain of subscripts can help you set up any relative velocity question. And this works out, right? The velocity of the car with respect to the ground was 100 kilometers per hour north. The velocity of the ground with respect to the truck. So the ground sees the truck going by at 90 kilometers per hour. But if you think about the truck is watching the ground move backwards past him at the same speed as moving forward. So the ground, according to the truck, the ground is passing underneath the truck at 90 kilometers per hour, but the ground is moving to the south. And if you were to add those two vectors together, you do get 10 kilometers per hour north. You get the same answer. But this form here, the second form, this chain of subscripts can help you more easily set up problems. So before we move on to relative velocity problems in 2 dimensions, so let's make sure we understand this pattern. So on the left side of the equation, you always have a single relative velocity. On the right side, you have vector addition, usually of just 2 when we keep things simple, but you can have more relative velocities, but you'll always have this chain. So you'll, for example here, if this is the relative velocity of a plane with respect to the Earth, that's the same as the velocity of the plane with respect to the air, plus the velocity of the air with respect to the Earth. And you have this chain. The A's and A's kind of connect, and it's almost like they kind of like, you can think of them as canceling out, and you're left with PE. So in this next example, you can think of that. Think of this just some general example with the letters matching up. C, E, and W. We're not exactly going to give any definition right now, but the W's wind up kind of like canceling out, and we chain up the C and E, and you get VCE. So we'll set up a couple of problems and apply this idea. So here's our first problem. We are going to look at an example of an airplane. So the airspeed of a small plane is 215 kilometers per hour. And the wind is blowing at 57 kilometers per hour from the west. So the wind is coming from the west and moving towards the east. We're going to determine the velocity of the plane relative to the ground if the pilot keeps the plane aimed in a certain direction. So we all understand this. A plane can aim itself in a certain direction, but if there's wind, the wind is going to blow it off course, right? And so in this question, we're finding what that new relative velocity is, what the speed of the plane would be, and what the direction of the plane would be. So think about what we're given. So a couple things we're given. So we're given the velocity of the plane with respect to the air. So kind of like in still air, if there was no wind, the plane flies at 215 kilometers per hour, and the plane is pointing in the direction 34 degrees east of north. We know that much. Now we also know the speed of the wind. Now the speed of the wind is the velocity of the air with respect to the ground. That's what that is. And it is 57 kilometers per hour. And we'll be careful with the direction here. It's from the west, which means it's blowing perfectly east. And we're asked to find the velocity of the plane relative to the ground. That's what we're trying to find. So we have a two-dimensional kind of like vector problem. We have two methods to do it. However, I think this one, the diagram is easy enough that I think the trigonometry method lends itself to this problem. So I might add here, VPG, it is what we're trying to find, but can you form the chain, the subscript chain that gives us that result so we can draw our diagram? VPG would be VPA plus VAG. The A's kind of match up, form the chain that gets us VPG. So what's VPA? 215 kilometers per hour, 34 degrees east of north. So something like so. 34 degrees, and I'll say 215 kilometers per hour. And the wind is blowing at 57 kilometers per hour to the east. So VPA, we're adding VAG, so tip to tail, we'll add it going this way. So this is not to scale for sure, but that would be going east, 57 kilometers per hour. And the resulting vector, I'll use a dashed line here, is what we're trying to find. This is VPG. So we want to know what the length of that is and the angle. So we'll be interested in finding this angle right here. So yeah, we've set this up, guys. We just got to use trigonometry to finish it off. Now, we have two sides in this triangle. We do need to get a third angle. So there's multiple ways you could think about it. I might think of it this way. Since we know the wind is actually blowing perfectly to the east, this little dashed triangle I have is a right angle triangle, north and east, and that's 34, 90. This angle in here would be 56. And because straight lines are 180 degrees, what's left over here is 124 degrees. And so now we have a triangle with two sides, an angle, and we're old pros at this. We can use the cosine law to find the magnitude, and then we'll use the sine law to find the angle and direction. So if you want to, pause the video, do it yourself, fast forward afterwards, that'd be no problem. So what is the velocity, or at least the speed? The plane is moving with respect to the ground. So we'll set up the cosine law. Be the big root of 215 squared plus 57 squared minus 2 times 215 times 57 times the cosine of 124. So let's give that a go, see what we get. 215 squared plus 57 squared minus 2 times 215 times 57 times the cosine of 124, big square root. So about 251 kilometers per hour. Which, if we just think about this and use some common sense, I can buy that. The plane was flying in kind of a northeasterly direction, and the wind is kind of helping it along, blowing east. So it does make sense that the speed of the plane actually increased a little bit. What's the angle? So sine theta over 57 is equal to the sine of 124 over 251. So theta will be inverse sine of 57 times sine 124 divided by 251. Let's get that angle. 57 times the sine of 124 divided by 251. So I got about 11 degrees, we'll say. And so now we can answer the problem. The velocity of the plane with respect to the ground. So this would be the speed and direction that somebody just watching the plane fly by on the ground would see it moving in, is the following. It's 251 kilometers per hour in this direction. And maybe you want to think about what the direction is. I can tell you the direction is not 11 degrees east of north. If we look at our diagram, we have that the velocity of the plane with respect to the ground is 11 degrees from the 215 kilometer per hour vector, the velocity of the plane with respect to the air. It's 34 degrees plus an additional 11 degrees. It's 45 degrees. And that's 34 plus 11. And east of north. Now, 45 degrees east of north is pretty much northeast. So if you were to say northeast, that's fine, because that means exactly 45 degrees east of north. And we've done our first relative velocity problem. So we made sure we knew what we were finding and set up the chain of subscripts so that we knew how to draw the vector diagram, and then just use trigonometry to finish the problem off. Let's do one more example. So this one, the math will be a bit easier because we'll be using strictly right angle triangle trigonometry. So here we have an Olympic canoeist, and something got lost in translation here. So they can move at 4.5 meters per second in still water. So if they were on a lake, this should just be 220. So if this canoeist, say, was on a lake, completely calm, then they could travel at 4.5 meters per second. But, if there was a current and the current was kind of helping them on, then we know they could probably travel faster, for some observer looking at them from the shore. But in still water, they can travel 4.5 meters per second. And they're crossing a river, and this river has a current that's traveling east, 3.2 meters per second. So if the canoe aims north, so we all understand that the canoe can aim itself north, but if they're aiming itself north, the current is going to kind of move them in an easterly direction. And they're actually going to move across the river in some direction, kind of north and kind of east. So let's find the velocity relative to the shore. So let's set this up. What are we given? The canoe can travel 4.5 meters per second in still water. And it's aiming, the canoe is aimed northward. So the velocity of the canoe with respect to the water is 4.5 meters per second north. We are also told that the current, the river, is flowing at 3.2 meters per second east. This current is the velocity of the water with respect to the shore. So I'm going to use S for shore. That's 3.2 meters per second to the east. And we're asked to find the velocity of the canoe relative to the shore. And setting up our little chain, that will be the velocity of the canoe with respect to the water, plus the velocity of the water with respect to the shore, i.e. the current. And that's what we're trying to find. So having set this up, I don't feel the need to maybe redraw the diagram. I might just add on to the one that's here. So this is 4.5 meters per second. The canoe aims itself up, but the current is moving it more to the east. And let's wrap this up. So the size of that velocity vector we can get using Pythagorean theorem here, because it is a right angle triangle. So the root of 4.5 squared plus 3.2 squared, we'll get that. And the angle we can get by using tan. So in this diagram, the opposite side is 3.2, and the adjacent side is 4.5. So let's do those two things, and then we can kind of make a concluding statement. 4.5 squared plus 3.2 squared. So I got about 5.5. And the direction, 3.2 divided by 4.5. Tan. Call that 35 degrees. And so the speed of the canoe with respect to the shore, so for an observer on the shore, in their frame of reference from the shore being stationary, they would actually see the canoe moving up across the river and to the east. As far as the canoe is concerned, they're pointing straight north. But yeah, the current's going to blow them to the east, and some person on the shore is going to see that canoeist drifting down. So we have 5.5 meters per second, and our direction is 35 degrees east of north. And we've got it. So we're going to look at just going to tweak this problem around. So we know if the canoe aims north, it's going to be kind of swept to the east. But what if the canoeist wants to actually, finish directly across the river? What if they want to aim north? I think hopefully it makes sense to you that if they want to finish north, they've got to kind of paddle upstream a little bit, so the current is going to blow them back so that their motion is straight across the river. So it's a worthwhile question to ask, what direction should we aim the canoe to actually finish where we want? So that's what we're going to do in part B. If the canoe landed directly across from the starting position, at what angle would the canoe have been aimed? And so you can see we have the vector diagram there. It's just the same situation we had from before. The velocity of the canoe with respect to the shore is the velocity of the canoe with respect to the water, plus the velocity of the water with respect to the shore. That's already been done for us. And we know two of those three things. And note, we're not asked to find what, we know by setting this up, we are going to have the motion straight across the river. So the speed of our canoe with respect to the water is still the same. It's still 4.5 meters per second. The canoeist hasn't got any stronger or weaker. That's what they can paddle in still water. The current is still 3.2 meters per second. But we set this up so that the motion will be straight across the river. We need to find that angle. So in this case, we actually have the hypotenuse in the opposite side. So we'll set up the sine ratio. Sine of angle phi from our diagram is opposite 3.2 over adjacent 4.5. So we'll do that division and do inverse sine. And let's see what we get. 3.2 divided by 4.5, shift sine. So, basically 45 degrees. I got about 45.3. So the canoeist in their boat in the direction. So the diagram we have has the angle being west of north. So we'll say 45 degrees, and this is west of north, or northwest, if you prefer, since it's exactly 45 degrees. If you'd like to, and just maybe as a quick aside, if we wanted to find what the actual relative speed of the canoeist with respect to the shore is, we could use Pythagorean theorem again. Here we would do 4.5 squared minus 3.2 squared. So I didn't ask for this, but might be interesting to do anyway, really quick. Doesn't take too long. And you get about 3.2 meters per second. So in this scenario, if the canoe aims itself kind of northwest, the current will blow it so that its path is pure north, and the canoe is actually slowed down a little bit, which actually makes sense too, right? If the canoe is paddling upstream, the canoe is actually going to kind of slow it down, because the current is actually acting. It's kind of opposing its motion. So it made sense we got kind of a smaller value. What you guys should be able to do after this lesson is, if given your own relative velocity example, you guys should be able to, looking at what's given and looking at what's required, you should be able to set up the problem and set up your own kind of equation with your subscripts matching up. That will help you draw out your problem. In this case, we had a diagram. In the previous question, we made our own diagram. And then you guys should be able to use trigonometry to finish it off. You should also be able to apply this idea of chaining subscripts in one dimension too, and solve problems like the sports car and truck example. So what's next? So we're actually going to consider our discussions on motion in 2D finished for now. We actually are going to be analyzing uniform circular motion in 2D, and that is part of the 2D motion unit. However, I like to look at that in the context of gravitation and celestial mechanics, how the solar system works, how black holes work, satellites around the Earth. So I prefer to look at circular motion then. So for now, we're going to consider our 2D motion finished. And to kind of wrap up our first unit, we're going to look at dynamics in 2D. So we've looked at kinematics, the study of motion. Now we're going to look at dynamics, so the study of the forces that cause that motion in 2D. In our next lesson will be kind of a review of Newton's 3 laws of motion, making free body diagrams, doing some simpler problems in 2D. And then we'll, in our next day, we'll look at problems involving pulleys, inclined planes, friction. It should be a lot of fun. All right, I hope you guys are staying well. Have a great day, and we'll see you soon.